Here's an example that deals with rolling friction. A ball is rolling with an initial speed of 5 meters per second. It rolls to a stop over a distance of 8 meters. So here the initial velocity is 5 meters per second, and it rolls over here, gradually slowing down, and ends up over here 8 meters away. We're told to find the coefficient of rolling friction between the ball and the floor. What we're going to need to do here is use the equations of motion from from earlier in the year, from the first few chapters, to find the acceleration. Then we'll use the acceleration to find the net force. And from that, we can find the friction. So there'll be 3 steps here. So first, I'll take note of what I know. I know the initial velocity is 5 meters per second. It rolls to a stop. So the final velocity is 0, and it does so over a distance of 8 meters. So my change in position, or my displacement, is 8 meters. And I can use this equation. V squared is V0 squared plus 2a delta x. And I know the initial and final velocities, and I know the position or the displacement, so I can find the acceleration. If I do the algebra, a is v squared minus v0 squared over 2 delta x. And I can put in some numbers. That's 0 minus 5 squared, which is 25 meters squared per second squared, over 2 delta x. The delta x is 8 meters, so 2 times that is 16 meters. And you can see one of these meters up top cancels out with that one. And I'll be left with meters per second squared. And 25 over 16 comes out to 1.56. So the acceleration is negative 1.56 meters per second squared. And the negative here means to the left. If I have said the velocity is moving in this direction to the right, and it's positive 5 meters per second squared, then I have decided already that to the right is positive. So this negative sign indicates the acceleration is to the left. Once I know the acceleration, I can think about the forces. And here's an important little piece of physics analysis that you should understand. F net equals ma. In this case, here are the forces. Friction is slowing it down. Gravity is pulling down, and the normal force is pushing up. So mg is gravity, and n is my normal force. Those are equal and opposite, and n equals mg in this case. My net force, though, if these are equal and opposite, my net force is just going to be little f. So instead of saying F net equals ma, I can say little f equals ma, because in this case, the net force is the force of friction. And force of friction is always mu times n. So mu times n equals ma. And in this case, n is equal to mg, so I get mu mg equals ma. And you can see we have a m on each side, which cancels out. That allows us to solve this problem, canceling out the m's like that. And whenever we have something like this where a ball is rolling to a stop or something is sliding to a stop, the m's will cancel out. That means that mass doesn't matter. It doesn't matter if it's a big ball or a tiny ball. Mass cancels out of the equation. It will be the same in either case. What we're left with is this. Mu times g equals a. We're told to find the coefficient of rolling friction. There it is, mu. Algebraically, we can just divide each side by g, and we get mu is equal to a over g. And we can find this because we found a earlier. The negative here doesn't matter. The negative sign on the acceleration just indicates the direction of the acceleration. Friction would be the same number, the coefficient of friction, regardless of which direction we called positive or negative. So we can just put in 1.56 meters per second squared over g, which is 9.8. meters per second squared. And you can see the units entirely cancel out, leaving us with just a number, which is what we should get for mu. Mu has no units. And in this case, 1.56 over 9.8 gives us 0.16. That's the coefficient of rolling friction.